All right, today we're going to start with section 6.1, which is the set of rational numbers. And as we begin this, just throw it out there that for some people this is the most difficult chapter because you have had bad experiences with this content in your history. So in particular, we're looking at fractions, okay? So fractions are any number that is written in the form A over B, where B, the number on bottom, is not 0. So even if the number is 3 over 1, and you could simplify it to just 3, we would consider 3 over 1 a fraction, all right? The numerator is simply what we call the number on top, and the denominator is the number on the bottom. And rational numbers are any numbers that can be written in the form A over B, where A and B are integers with B not 0. So again, for example, we would say that the number 3 is a rational number because it can be written as 3 over 1. You can do the same thing with decimals. 4.7. 4.7 is a rational number because it can be written in the form of 47 over, I was about to say it wrong, 470 over 10. Yeah. Or 47 over 10, that's the one I want, 47 over 10. So as long as you have the ability to write it in a fractional form, it is considered a rational number. There are several examples or uses of rational numbers. So one way to use rational numbers is to solve an equation. So it's a solution. So to solve an equation like 2x equals 1. If we're only allowed to use integers, there's no solution for this because 2 times 0 is 0 and 2 times 1 is 2. So we went from 0 and jumped right over the number 1 that we wanted it to be and jumped to 2. There's no solution. But if we're allowed to have fractions, then the fractional solution to this problem would be the number 1/2 or 0.5. So one way and one use of rational numbers is just a solution to an equation. A second one would be considered a partition. So for example, 1/4 of my paycheck goes to rent. Okay? So you take something that is considered a whole and you take a portion or a partition of it out. That's a fraction. A third way is considered a ratio. So an example of that would be something like this. The teacher-student ratio is 1 to 12. And you could write that ratio like that as 1 over 12 as well. And the fourth one, is a probability. So an example for a probability would be something like this. When you roll a die, a regular fair die, okay? You have a 1/6, 1 out of 6 probability of rolling a 5. And later on in this class, we will talk quite a bit more about probabilities. We'll actually do a whole chapter about probability. It's a very big topic. These are 4 different uses for fractions. There's some different ways that we can describe or draw fractions too. So you guys have some pictures on your paper that should match up with mine, do they? Fantastic. Okay, so for each of the following pictures, I'm going to let you just write a number down for right now. I would like for you to write down a fraction that represents the shaded portion. Okay, if you make a mistake, we can always scratch it out or erase it and rewrite it in a minute. So write down the fractions that you believe represent the shaded portion of each picture. Okay, after you have an answer, I'd like for you to make a friend. Turn to somebody close to you. You're the furthest away, so you might have to shift back to talk with someone. Find someone, one or two people close to you, and just kind of see what your comparisons are. If they differ, chat about it a little bit. If you can't decide who's right or wrong, that's okay. You can start by saying, "Hi, my name is." That's a nice way to start a conversation.
Yeah. Okay. You do the same thing. Yeah, I was trying to figure out, I didn't even know about it. I didn't even get to the it's just sort of opinion of it. Yeah, so this
Okay, you all quieted down, so you must have come to some sort of resolution on your problems. What'd you guys choose on part A? 1/6. Do you think that there's anything else that a child might say this answer would be?
I said 1/4.
You said 1/4. Yeah, that's a common mistake. Okay, so if you said 1/4, why?
Because there's only 4 squares.
Yeah, there's 4 things, right? And one of them shaded in. So what's the misconception, now that you've talked with somebody nearby you, about why that isn't the case? Why is it 1/6 and not 1/4? Yeah, the parts are not equal. So I heard over here, because Brooke's voice, I heard your voice loud enough, saying that she did this. That's what you're saying, right? Yeah. So she made the parts equal, and then after she made the parts equal, she could actually make a claim that it's 1 out of 6. Does that make sense? It's okay? Okay, good. How about B? Did anybody say 1/5?
I did.
You did? Yeah. Probably if you said 1/4, I mean, this one's less clear the way it's drawn in, right? Than the first one. I mean, it's less, you're sort of led down the wrong track even more easily than on the first one. It's not actually 1/5. What is it? It's 1/4. And again, the problem is that not all the pieces are the same size. So if you restructure the pieces to be the same size, and you use my red lines as a grid marking, the blue is actually 1/4 of the full rectangle picture, right? So it's actually 1/4. How about on C? 2/7. Do you have any idea how hard it is to draw 7 equal pieces of a circle? It's actually pretty tough. Yeah, it's not easy.
It's usually 8 pieces.
Exactly. Yeah, you usually see 8 pieces or 10 pieces, right? Okay, so this one actually on part C is part of a whole. We kind of think of that as being a portion of a whole piece, right? We might get blown away. D is different though, because D is not like a whole connected picture, right? It looks actually quite a bit different than all the others, but all the pieces are in fact the same size. So what is the ratio that you got on this one? 7/12. Very good. So we can still count the pieces, and so we can actually, imagine that this is a whole puzzle or something like that, right? And we can count the number that are shaded compared to the number of all the pieces total. Good job. Okay, so a few historical facts about fractions. The Egyptians are actually one of the first societies anyway that we know that they used fractions. They used fractions that had numerators of 1. So they would not have expressed a number as 7/12. They would have written it as something like 1/4 plus 1/3. It's just how they did it. That's Sounds really difficult to me. The Greeks, they adopted fractions with denominators of 60 from the Babylonians. We still see this used in measurements of angles. For those of you who have not had number theory yet, which is totally fine, in number theory, we learn that what we call our numeration system, the way we do our numbers and our methods, is called the Hindu-Arabic numeration system. So if somebody goes freaking out and telling you that they're using Hindu-Arabic in the schools, you can just be rolling your eyes right then, because yes, they are. That's absolutely true. That's what we call our system. It's the Hindu-Arabic numeration system. The Hindu are actually the ones who developed the modern bar that we used between the numerator and denominator. And it came into Europe in the 1500s. Okay, so a little bit of some history behind how we got to where we are. So I'd like to show you some models then. I've already made mention of this a little bit. There are 3 models that we're going to focus on for fractions. One is called an area model, and you saw 2 examples of that, part A and B. Those are area models. So for an area model, you could have something like this. So I'm going to do the example of 3 over 4. So draw yourself your rectangle, and kind of like we mentioned before, dividing things into evens are super more friendly than odds. So we have it in half and in half again. And then we would shade in 3 of the 4 pieces. So this is an area model. Another model is the number line model. I'm going to continue to use the 3/4 on all my examples, it looks like. So in a number line model, you're going to draw a line, or a line segment really. It's going to start at 0, and we are going to end it at 1, just because our number is between 0 and 1. And again, nicely enough, because the number is 3 out of 4, we can divide this in half and in half again. I'm not going to label all the pieces, but the first piece here would be 1/4, the second would be 2/4, and the third one, which we care about right now, is 3/4. So this is 3 out of 4, and we would mark it with a dot on the number line. That's 3/4. So I didn't have a picture of that one before. I had a picture of the area model from the front, or the top, and I also had a picture of what's called the set model below. So the set model is the use of chips where some are shaded. So if you're using the set model, and we have the number, again, examples 3/4, then what you're going to do is the denominator tells you how many chips to draw. You're going to draw 4 chips. The more accurately you can draw them, the better, but you know, we're just going to do our best. And then you're going to shade in 3 of them. So that's 3/4. We're going to come back to our models when we talk about addition and subtraction, which is in 6.2. Addition and subtraction is more difficult than multiplication and division with fractions. Just the computations themselves are more tedious. But conceptually, they come right back to these area, especially the area models. But they come right back to our models, and you can see evidences of them with the models really clearly as to why the processes work the way they do. So we're going to come back to this idea in a later section. Fundamental. Anytime you see something that says a fundamental law, it means it's really important. So the fundamental law of fractions says, let A over B be a fraction, and n is any non-zero integer. If you multiply that n on the top and on the bottom of the fraction's overall value remains unchanged. Now, it's not necessarily present in the way that this is worded, but the reality is that it works for division too. If you divided the top and the bottom by the same number, it would create another equal fraction. And that's what we do when we work with simplest form. Simplest form, a rational number A over B is in simplest form if the b value is positive, so if there's a negative, the negative's on top, and the greatest common denominator, or divisor is what your book's using, greatest common divisor between a and b is 1. In other words, you can't divide them both by the same value and make them smaller. And still have integers. So no common factors greater than 1. All right, so we're going to do an example of that. We're going to take a fraction. Example number 2 is the fraction 7 over negative 14. And we're going to write 3 fractions that are equal to 7 over negative 14. So this is one of those places where, like, we could actually all come up with completely different answers and all be completely correct. Okay, infinitely many answers, so to speak. So I would like for you to write on your paper 3 fractions that are equivalent to 7 over negative 14. If you get stuck, it's okay. 3 fractions, and then turn again to the same neighbors you were talking with before and see what you can come up with if you're stuck. Okay, did everybody come up with exactly the same answers? No, that's not a surprise, actually. So somebody give me one number that you wrote down, one of your fractions.
14 over negative 28.
14 over negative 28. I agree. How did you get that from the first fraction that we were given? You doubled the top and doubled the bottom. Perfect. Somebody give me another one.
Negative 1 over 2.
Negative 1 over 2. So you actually did 2 things to get that one. Tell us what you did.
I simplified it and then I just switched the negative.
Okay, so you divided the top and the bottom each by 7, right? And then you moved the numerator, you moved the negative to the numerator instead of leaving the denominator. That one works. Give me another one.
21 over negative 42.
21 over negative 42. Oops, get that fixed. Okay, and how did we get to that one? What'd you do?
Multiply by 3.
Right, multiply the top and the bottom by the number 3, exactly. So be careful when we use language that you didn't really multiply it by 3, right? You multiplied it by 1, because 3 over 3 is 1. But you used a 3 as the multiplication factor on the top and bottom, which is just a little difference. All right, let's do one more. Does anybody have one more example that they did?
Can you explain the middle one again?
Sure. So on the middle one, what she did, there's 2 things. She divided by 7, top and bottom, like this, which would have given you 1 over negative 2, like that. And then 1 divided by negative 2 is actually the same as negative 1 over 2.
So could you technically, is 1 over negative 2 still a proper
Yep.
answer?
Yep, you could do 1 over negative 2. Sorry, I don't know names yet.
Danielle. Sorry,
Danielle.
I haven't taken math in years.
It's okay. Do you have a question, Danielle?
Did you mention that you couldn't have a negative on the bottom?
You can't not have a negative on bottom. We talked about simplest form over here, and in simplest form, there aren't negatives on bottom. So when Brooke did hers, she actually turned it into what we would have called simplest form. Yeah, but there's nothing that said on this problem it had to be in simplest form. Good questions. All right, interestingly enough, you also could have any fraction that's equal to any of these. So for example, if I know that negative 1 over 2 works, it actually means that negative 2 over 4 also works. Although getting from this to this doesn't look very obvious, right? But if they're both equivalent to negative 1 over 2, then they're both working as well. So other facts. All right, one more example. We're going to talk about simplest form on this one real quick. Simplest form means that they are able to be reduced by the same factors. So if you're taking a look at this one, it has 42 squared over 35 squared. The problem, if you will, is that you can't cancel operations. Squaring is an operation. It's not a number that's affecting the values in the same by the same value. It's an operation, not a number. So, for example, what I mean is this. Squaring means I have 42 times 42 on top and 35 times 35 on bottom. I didn't multiply them both by the same thing, right? So I can't cancel out squares. But what I can do is I can simplify fractional values. So when I take 42, hopefully you remember that 42 is 6 times 7. Shake your head if you remember that. Yeah? How about 35? It's 5 times 7, and there's 2 of those. So what the simplification, this fact over here said on the very bottom, is that once I get all of the factors sort of written out, they don't even have to be completely factored out. Obviously 6 is 2 times 3. But I don't need to care about that, because as soon as I have a 6 measuring with a 6 on bottom, I would be able to cancel them, okay? But I don't have those, but I do have 5s, I mean not 5s, I do have 7s that cancel from the top and bottom. So what I end up with on this problem is 6 times 6, and yeah, they do break down into 2s and 3s, but 5 doesn't on bottom, right? I can't break the 5 apart into anything that will simplify with what's on top, so I'd simply multiply them back together, and the result would be 36 over 25. And that would be my simplest form on that one. Okay, so we will pick up next time with theorem 6.2. You don't have any homework. You don't have to do anything for me, except I would advise you between now and Friday to go and print out some more notes. Okay? Have a great week, guys.